Hey, everybody. So today, the main topic is going to be about units. But before we get to that, I want to just say a few brief remarks about class groups. So you're probably sick of computing class groups by now, but they're pretty important, but you might, and somehow they might not seem so important yet. So I wanted to say a few things just to explain why you spent so much time last week computing them and computing examples. So, and one thing we did talk about is they control unique factorization. That's sort of how we motivated things. So let me just put that up there. So not only they sort of control whether unique factorization happens, but they sort of really give you some measure of the discrepancy from unique factorization holding. And again, we'll come back to that and actually sort of use that in an interesting way later. Let me say something we haven't talked so much about. Maybe I've alluded to it once or twice, but the other thing they do is they control the abelian extensions of K. So the class group of K sort of controls the abelian extensions of K. Well, that's not quite true. The class group of K sort of controls certain abelian extensions of K, and then there are sort of generalizations of the class group that control sort of other abelian extensions. You can sort of put that all together, you get something like the class group that controls all abelian extensions. So this is the subject of class field theory. This is a pretty interesting theory. So for example, if you sort of carry this out for just the rational numbers, you see that all sort of abelian extensions are contained in some cyclotomic extension. But sort of there's sort of a massive generalization to this, and somehow, I mean, sort of the point in this example is that sort of the cyclotomic extensions are sort of, their Galois group is Z mod MZ cross. It's like sort of the Galois group of Q zeta M over Q. This is sort of canonically isomorphic to Z mod MZ cross. We're going to talk about that more actually next week. So if you took sort of algebra with me, then you know this fact, and otherwise we'll recall it next week anyway. But somehow what's interesting about this statement is this is sort of a Galois group that controls all abelian extensions of Q, it turns out. And somehow it's described internally in terms of like the arithmetic of the integers Z, sort of just the units and sort of the quotient Z by some ideal. And this picture sort of generalizes to any sort of field K. So it's not sort of just controlled by sort of like OK cross mod, like OK mod sort of some ideal cross, but it is sort of controlled by sort of things related to the class group. So this is sort of some general, the Z mod MZ cross you sort of view as being some generalized version of the class group. Okay, so anyway, so that's something we haven't talked about so much yet. We're going to start to see some examples that move towards this. And we're not going to do class field theory. That's sort of the topic of the second class in algebraic number theory. We're going to do some examples related to it. So there are some examples that explain some connections with what we've done so far on the worksheet this week. And then there'll be more of that next week as well. Okay, so look at this. That's another reason we care about them quite a bit. But for me, that's the main reason I care about them. But there are lots of different reasons different number theorists have to care. Okay, so that's another reason to care. I want to say sort of now just a little bit more about like the kinds of things we know and don't know. And sort of turns out like even in sort of there are simple things, and that's sort of the story of number theory. Like there are simple things to say that we don't know. So sort of one thing we do know. So we know sort of which imaginary quadratic fields have class number 1. Let me sort of start right. So often we write 8, sort of the class number of K, so that's the order of the class group, is So this is just means the size of the class group of OK. We write sort of, yeah, we write that class number as H sub K. That's H for Hilbert. So Hilbert introduced a lot of these ideas, was very influential in sort of the development of class groups and sort of related theory. Okay, so we know which imaginary quadratic fields have H equals 1. So on the worksheet last week, you sort of, one of the exercises was to sort of check this list. They all have class number 1, and then a much more difficult thing is to go in the other direction and show there aren't any other ones class number 1. But sort of in that direction, we actually know quite a bit more. Like we know sort of if you sort of fix some number D, there are only finally many imaginary quadratic fields with class number D, and it's sort of almost effective to compute them. And or maybe it is effective. Yeah. So, okay. Well, yeah. It's almost or just is effective to compute them. Good. So this is like something you could sort of redo this with sort of 2 here instead of 1, and there'd only be finally many. And sort of in principle, you could sort of come up with a list and so on. Great. So imaginary quadratic fields are actually in pretty good shape in some sense. And there are other things we don't know. So even though we have procedures for sort of computing things like certain sort of statistics of sizes are still open. So there's sort of a sort of answer we guess is true for these things, governed by something called the Cohen-Münster heuristics. So then those are heuristics are not facts. So anyway, so you could ask like, how often does 3 divide? Like what percentage of sort of number fields of quadratic extensions of imaginary quadratic fields? Let's say, what percentage does like 3 divide the order of the class group? And that's sort of something we have we sort of know what should be true, but we don't have a proof for that. Okay. Should be careful about stating specific facts, because some facts, like, I guess maybe we do know, but in general, sort of this kind of thing, like sort of you can sort of phrase that for other primes, and like this is sort of something we don't know the answer to in general. Okay, so I mean, that's a simple question we don't answer. And then for real quadratic fields, it's not even that we just don't know, not even that we just don't know the sort of the statistics, so we actually don't even know like anything. So sort of for real quadratic fields, we expect but don't know that infinitely many have class number 1. Of course, and real quadratic just means you're taking the square root of a positive real number, and imaginary quadratic means you're taking the square root of a negative real number. Right, but so for real quadratic fields, we don't know whether there are infinitely many with class number 1. I mean, it looks like there should be. You keep on computing them, you keep on finding them, but yeah, well, we don't know. So anyway, there are lots of sort of interesting questions here. Leaving quadratic fields are somehow the simplest thing besides Q, so sort of shows the depth of our ignorance. Let me just say one more thing that we're going to come back to. So we're going to study the class numbers of the fields Q adjoins zeta P. So you add in the P through to unity. So it's known that these are equal to 1, known as sort of the class number is equal to 1 if and only if P is less than or equal to 19. So P is prime. Yeah, and it's known, and there are reasons that they get pretty big pretty quickly even. And somehow in the end, we're actually in like, what we're more interested in will just be whether or not P divides it, and we have sort of some idea like how often that happens, but again, sort of it's not proven. but this is sort of the thing that's related to Fermat's last theorem that we're going to come back to and talk about. So again, this is something we'll talk about a little bit more next week, and then sort of more towards the end of the class. Okay, so right, so I just wanted to sort of say, like, there are lots of interesting things about class groups. Like, there's a reason we spent so much time just computing some examples and sort of understanding how you compute examples. It's because they sort of show up all over the place. Okay, so right, but that's not what we're talking about today. Today we're talking about units. So K over Q is K is a number field, so finite extension of Q. We want to know what is OK cross. So that's just in OK is the ring of integers in K, so that's a ring, and then OK cross just means the multiplicative units. This means just multiplicative units in OK. So there are elements of OK whose inverse is also an OK. Of course, I mean, an element of OK always has an inverse in K. The trick is whether that inverse is in OK, is also an integer. That's sort of not usually true. Okay, so that's the question. Oh, and let me just notation. Like if you look in Milne, he calls this U sub K, and I think some other sources also use that. So U sub K is the units in OK. I prefer just sort of the standard notation. If you have a ring R, then the units in that ring are R cross. Okay, so I mean, well, this is an important question for lots of reasons. I mean, maybe the simplest way to motivate it right now, though, is just so this is the other part of factorization. I mean, somehow, like when you have unique factorization, like it doesn't tell you you sort of have a unique expression as a product of irreducibles. Like it tells you have sort of a unique expression as a product of irreducibles, sort of up to multiplication by a unit. And so sort of somehow if you want to understand how factorization works, like in the case where you do have unique factorization, then you want to understand what the units are. But it also sort of comes up, I mean, somehow, I don't know, if you're writing down principal ideals, you want to understand sort of like what is the ambiguity between sort of different things that generate the same ideal. Like you need to understand what the units are. And sort of, well, I mean, this is important because I mean somehow it controls whether you have canonical, yeah, like it controls whether you have sort of canonical generators and for principal ideals and sort of things like this. And so it sort of it can make some computations either more complicated or less complicated, sort of depending on whether you have units or not and sort of how they behave. So it's sort of an interesting and in the end important part, like an important part of the structure of a number field to understand. But okay, luckily we can understand them. So let me just recall something we saw earlier. So if we have alpha in OK is a unit, if and only if the norm from K to Q of alpha is equal to plus or minus 1. Okay, so right, and there are different ways to think about this, but one direction was, so yeah, so this came up on one of the worksheets. One direction is very easy, and if you have a unit, well then the norm map is, well, and so it's in OK, so the norm lands in OK and in Z, but sort of if it's, and this the norm is multiplicative, so if it's a unit here, then its image is a unit in Z, and the only units in Z are plus or minus 1. So that's sort of why if you are a unit, you have to have norm plus or minus 1. On the other hand, you can either think of the norm as like being the product of the conjugates, and okay, so you sort of take the product of other conjugates, and that gives you an inverse, or you can think of just like the minimal polynomial for alpha and sort of what the norm is doing in sort of in terms of the constant coefficient, and use that to sort of see that when a norm is 1, you have an inverse. So there are a couple of different ways to think about this, but okay, so this is characterization. Okay, and this sort of forms the basis of our study because, I mean, this norm, like, it's just a polynomial equation. So, so example, in q square root of m, so let's do m congruent to 2 or 3 mod 4. Then sort of the units in the ring of integers, which is just z squared of m, because m is 2 or 3 mod 4. That's the same as just solutions in z times z squared to a squared minus b squared m is equal to plus or minus 1. So because this is the norm of an element, a plus b square root of m. Okay, so and somehow when you're computing units, you're just solving this polynomial equation. So in that sense, like, it's a straightforward thing. I mean, it's very concrete what you have to do. But on the other hand, I mean, well, unfortunately, it's a polynomial equation. Like, I mean, polynomial equations are, it's how you don't, they're not always easy to solve, and especially sort of into integers. So, I mean, it's not completely clear whether this is going to be an easy problem or not when you look at it. And it's not like you got a linear equation you can just really easily solve. I mean, you got a polynomial equation and you're sort of solving in the integers, so it's not 100% obvious. But okay, we can say some stuff just to get started. So let's look at like q square root of minus 17. Well, then we're looking at a squared. So this sort of m, when m is negative, this minus sign sort of gets turned into a plus sign. So we're just looking at a squared plus 17b squared equals plus or minus 1. Okay, well, that's pretty easy to solve. I mean, this implies a squared means sort of b has to be equal to 0, and a is equal to plus or minus 1, and then we're sort of only going to get 1 here. So the units in z square root of minus 17 are just sort of, well, they're the same as the units in z, they're just plus or minus 1. Okay, so I mean, somehow the same thing's going to work whenever m is negative. Like, in general, if m is less than 0, then and not even if m is congruent to 2 or 3 mod, just 2 or 3 mod 4, like, also sort of is here congruent to 1 mod 4. You'll just sort of change the equation a little bit, and you'll be looking not just in z squared, but maybe z over 2 squared. But okay, anyway, so if m is less than 0, sort of there are only finitely many solutions. To this equation, and sort of usually just plus or minus 1. So the first exercise in your worksheet this week is sort of to just do this precisely, but I mean, somehow almost, you see here, as soon as m gets big enough, and sort of you have a little bit more, you have more wiggle room when m is congruent to 1 mod 4, so you have sort of wiggle room then, but in general, sort of once this is big enough, so you can't get 1 here. So this part has to be 0, and then you just get plus or minus 1. Okay, but otherwise, I mean, when you get only finally many, well, sort of just even without working out which ones you can get, and you can sort of really concretely do this, and you'll do that. But even so, if you know there are only finally many, then sort of well, it's a subgroup of finite order, like it's a group of finite order, so every element is a torsion element. But sort of being torsion just means x to the n is equal to 1. So all of these are going to be roots of unity. In particular, these are always roots of unity. Okay, so for example, like z adjoint I, like you have not just plus or minus 1, you also have I and minus I. And so those are sort of more units, but they're all roots of unity. Okay, so that's good, but this is sort of not as nice if we sort of leave this world. So let's look at a positive m. So let's look at q squared of 5. Well, then we're looking at a squared minus 5 b squared is equal to plus or minus 1. And well, and now it's suddenly not so clear what's going to happen, because I mean, well, depending on how you look at it, I know if I just stare at this equation, I'm not totally like, if I plug in a few values, I'll probably get lucky. But I mean, somehow if I just sort of see an equation like this, I wouldn't even be sure. I don't know. Well, maybe now I would, but I mean, somehow if you threw a couple more things on here, like I wouldn't be sure if this was going to have a solution or not. And then I also sort of wouldn't know like how many to expect. I mean, this argument doesn't apply before, and like sort of b doesn't have to be 0 because b is sort of a correcting term. So b sort of lets me get smaller. But then sort of I have these squares here still, and like, you know, polynomials are hard. So it's, I mean, you have to think to sort of understand how you actually can solve this thing. Okay, but well, okay, first we can just guess and check. And so we can just sort of start throwing in some numbers. Let's try a is equal to 1, b is equal to 1. So we'll get a squared minus, so we'll get sort of minus 4. And then let's try, okay, so that's good. A is equal to 2, b is equal to 0. So we got 2 squared is equal to 4. Okay, good. And now, we should do sort of the obvious thing, which is we should actually divide these two. And so we got two things whose norm was equal to 4. So, well, and there are only sort of finitely many ideals with any fixed norm. So if both these things have norm equal to 4, there's a reasonable chance that they are given the same ideal, in which case they would differ by a unit. So sort of this is what we can try. So let's sort of take the quotient. So we can always divide them in the field, and we just have to sort of check. We have to sort of check that the result is in the ring of integers. But in this case, sort of because 5 is congruent to 1 mod 4, this is an integer. And its norm, well, its norm is just the norm of the top divided by the norm of the bottom. So its norm is -1. Okay, good. So good. Well, that worked. So, and actually, this is basically how you do it. This is basically in sort of a strategy you can use to find units. Is you just start computing norms of things, and you sort of, well, some version of the pigeonhole principle is basically going to apply here. Like you're going to end up sort of hitting the same things, hitting the same numbers if you just start plugging in. And then like there are only so many times you can hit the same number because there are only, without sort of two things differing by unit, because there are only sort of so many ideals of a fixed norm. This is actually sort of, we're going to prove a statement about the structure of the group of norms, and this is going to be like the key idea in doing it. Okay, so this is, well, anyway, but so what we got is sort of this is an integer. So really when I say an integer, I mean sort of in OK, k is equal to q squared of 5. Okay, its norm is -1. And well, it's really not, I mean, this thing has infinite order. So it's not a root of unity. So it's not like the imaginary quadratic place. somehow we know it's not a root of unity because this field like can be embedded in the real numbers. And any field you can embed in real numbers, like, well, the only roots of unity in the real numbers are plus or minus one. So sort of if you have something that's not plus or minus one, it's not a root of unity. But if you have an element of if you have an element of finite order, then like that means it's a root of unity. So this has to have infinite order. That's one you can see. And on the other hand, you can just think of this being a real number, like think of square root of 5 as being positive real square root of 5. And then this number is sort of bigger than 1. So you can think, or this number is not bigger. Is this bigger than 1? This is probably less than 1. So this is square root of 5 is not as big as 3. Yeah, so sorry, the square root of 5 is okay, so I can't do basic math. Square root of 5 is bigger than 2, so 1 plus square root of 5 is bigger than 2. There's this is bigger than 2. Sorry, this is a positive. This number is bigger than 1. The numerator is bigger than the denominator. So this number is bigger than 1. Just if I think of it as a real number, and if I take powers of it, it's getting bigger and bigger. So I'm never going to sort of land back at 1. So this is sort of infinite order inside sort of this abelian group of units. And it's unlike the imaginary quadratic place, like it's really possible that you can have sort of infinite order elements, not just sort of roots of unity. And so there is some sort of complexity to the structure of units, sort of at least sort of in this example. And this will sort of turn out to be fairly generally the case. Of course, by the way, we just computed a single unit. So, I mean, computing one unit doesn't really tell you anything about the structure of unit groups. And here it told us the unit group was infinite order, but like we don't know if they're like if this sort of generates the unit group, or like maybe this with plus or minus 1 generates the unit group. We don't know sort of just from doing this, like maybe there are sort of many sort of independent units you have to find. Like, so this just found a unit. This doesn't tell you anything so far about how many units there are or what the structure of the unit group is. But okay, we have a theorem for that. So the theorem says the unit group is isomorphic to the roots of unity in K. So this means the roots of unity in K. Times z to the r plus s. So here r is the number of real embeddings of K, and s is the number, minus 1 of complex embeddings. Okay, so say more, and we'll prove this in a minute, but just what does this imply in the imaginary quadratic and real quadratic case? So just to connect back to these two examples. K is q squared of m less than 0, then there's no real embeddings, and then sorry, the number of complex embeddings over 2 is what s is always. So there's no real embeddings, and then there's two conjugate complex embeddings. So again, when I say complex embedding, I mean I'm embedding the complex numbers that doesn't factor through the real numbers, and those sort of coming conjugate pairs. Good, and so then, okay, so in this imaginary quadratic case, then OK cross is just the roots of unity in K, which of course we already discussed above. That just covers what we had. If K is equal to q square root of m with m greater than 0, then that implies r is equal to 2 and s is equal to 0. So there's sort of two real embeddings depending on whether you send m to its sort of positive or negative whether you sort of take the positive or negative square root of m. Okay, so that means OK cross isomorphic to the roots of unity that live inside of it times z to the 2 minus 1. So just you get one copy of z. The roots of unity, so we said this already, in a field that lives inside the real numbers, those are just plus or minus 1. In the field that could be sort of lives inside is sort of going to become confusing terminology. It's a little bit, it's sort of field that can be embedded in the real numbers. Your sort of roots of unity are containing the roots of unity of the real numbers, which is plus or minus 1. Okay, so this is the structure of a real quadratic field. So this sort of implies, so in particular, this applies to q square root of 5, which we were looking at above. And in this case, you can check sort of somehow once you have this theorem and you know the structure. Okay, well, you could do it so you could do it without having the theorem and knowing the structure, but it's particularly easy once you have the theorem and know the structure. You could check that this so the ring of integers here is really plus or minus 1 times this unit we wrote down, times the groups generated by this unit we wrote down earlier. So 1 plus square root of 5 over 2. So this is called a sort of fundamental unit. So in a real quadratic field, this theorem tells us there's always going to be sort of the unit groups are always going to be the form sort of plus or minus 1 times sort of a power of some fundamental unit. And we can really sort of pin that unit down uniquely by saying, somehow thinking of sort of square root of 5, like if we think of square root of 5 as being sort of positive roots, then we should require right, we should require this to be positive. Is that right? Okay, well, the exercise to think about how you pin this down uniquely. But okay, and so somehow if you don't pin it down uniquely, it's pinned down sort of up to its inverse. So what I probably should be saying is, right, so this should be sort of, there should be something of absolute value greater than 1 in here. Sorry, that's what I meant. Sorry, so you should pin it down by sort of taking the thing of absolute value greater than 1. Sort of if you interpret square root of 5 as being the positive real square root. And that sort of determines the unique generator of this copy of z in here. So it's okay, but if you, and just writing down a unit of infinite order is not enough to know it generates this. Like it could sort of generate some, like it could generate sort of the group. So it could be like the fundamental unit squared or the fundamental unit cubed or so on. Like just writing down an infinite order unit does not mean it generates this group. But okay, and somehow you could, in this case, and sort of in general, you can sort of write down ways to characterize sort of which one is going to be fundamental. Okay, and that's on the worksheet, so you'll see that. See that this week. Okay, so good. So how do we prove this theorem? Well, let me make one remark first, which is, and it suffices to prove actually a little bit of a weaker statement, and then yeah, so we don't, and what we actually need to prove is we just need to prove OK cross is finitely generated, and sort of its rank is r plus s minus 1. And actually, sort of somehow the torsion part is very simple. So, and sort of course, and arbitrarily, like a finitely generated Boolean group, its torsion could be very complicated. But when we already know the torsion is going to be roots of unity, because sort of that's what it means to be, like that's what it means to solve the equation a to the n is equal, or x to n is equal to 1. Like that means you're a root of unity. And we know the structure of roots of unity. And we know there can only be finitely many in a finite extension of Q because of this fact I wrote down sort of earlier. Like we know sort of the, well, not just the Galois, we don't need the Galois group here, but we know that the field generated by the M fruits of unity over Q, that this has sort of order the size of Z mod M Z cross. So the number of integers, this Euler function, the number of integers co-prime to M. And well, that sort of, as M gets big, that gets arbitrarily big. And so, and if you have a finite extension of Q, it can only contain sort of an extension of sort of size less than equal to it. And so sort of it can only contain this thing sort of for M, sort of some bounded M. So you sort of only have finitely many roots of unity, but then it's an easy exercise to check that if you only have finitely many roots of unity, then sort of the subgroup of all roots of unity is cyclic. And so somehow we don't need to do anything to prove the torsion part is sort of as we say. So then sort of once we know it's finally generated and has the right rank, the rest of this will come for free. Okay, so that's what we need to prove. So we need to show we know torsion is just summarize. We know this torsion subgroup is equal to the roots of unity in K and is cyclic of finite order. So we only sort of need to and basically we can just take the quotient by this and understand that group and show it has order, it's order R plus S. Okay, so that will come up in a second. Right, so there's two parts. Like there's two parts and like neither of them is totally obvious. The first part, and so it corresponds to like what I was saying about sort of this kind of equation. Like number one, like I don't know if there are any solutions. Like, so I don't know if it's big at all. I don't know, so just looking at this, I don't know that I can just find solutions to this equation. And then number two, like I also don't know that I can't find solutions. Like I somehow I don't know, I don't have any bound for like how complicated my solutions could get a priori. And so these are like the two problems we need to solve. Like we need to sort of produce enough solutions to get the rank we want, but we also sort of need to show there aren't too many solutions, like sort of that we're getting something finally generated. Okay, well basically, and so the second one's easier to solve, but sort of solving it also sets us up to solve the first one. So, so to show it's finally generated of rank less than or equal to R plus S minus 1, well, we're going to do the following. So we're going to take sigma 1 to sigma R. These are going to be the embeddings of K into R. So these are the real embeddings, and then sigma, let me sort of tau, actually, tau 1 to tau S are the embeddings from K into C. But we only just take one per equivalence class, sort of with complex conjugation. So just this thing I said before, the complex embeddings, the ones that don't factor through R, these always sort of come in pairs that sort of differ by composition of complex conjugations. So let me just take one in each pair. So this, and well, this is not new. This is sort of what we did when we were proving the class group was finite. Like this is sort of how we put the ring of integers into something we could understand a little bit better. And well, we're going to do the same thing here. What we're actually going to do is we're going to send OK cross to r to the s plus 1, or sorry, r to the r plus s minus 1. And we're going to send an element to the just set of the logarithms of these of its absolute values. So let me sort of call this map L. So I look at all these embeddings, and sort of after each of these embeddings, I can take just the standard absolute value on the real numbers or complex numbers. For the complex ones, I actually want to take sort of 2 times it for a reason I'll explain in a second. I mean, basically, just because I have sort of these 2 pairs. Okay, and so, well, so what do we know? So, let's make some observation about this map. So this is a homomorphism. So OK cross is a group under multiplication. Real numbers is a group, and this is a real vector space, or just under sort of its addition group law. And well, and why is this homomorphism? Like just checking each coordinate. So in this embedding sort of sends OK cross to R cross, and then taking the absolute value, sort of that sends R cross to just sort of positive real numbers under multiplication, and then taking the logarithm turns sort of multiplication into addition. So that's sort of why we have something additive over here. Okay, and sort of it sort of works the same way on all the coordinates. This 2 doesn't change anything. So multiplication by 2 is a homomorphism for real numbers to real numbers. That's okay. So a homomorphism. And so its image is contained in sort of the hyperplane. So x1 plus x2 and so on plus xr plus s is equal to 0. So this is just a statement. I mean, this is because the norm of alpha is equal to plus or minus 1 for alpha and OK cross. So the absolute value of the norm of alpha is equal to 1. And then sort of take log. So you expand as a product. So we know sort of the norm is the product over all embeddings. So there we'll have sort of tau 1 and tau 1 bar. But then when we take the absolute value, you just sort of get 2 times the absolute value squared. But okay, and then you're going to take log. So and that's where this 2 comes from. If you expand the product and take log, you get this identity. So, I mean, somehow this is, yeah, so sorry. What I wrote down up here was bad. So the map I wrote down goes to R to the R plus S. So we have R real embeddings and S complex embeddings. R real embeddings, S complex embeddings. So this goes to R plus S. Where this minus 1 is coming from is because we factor through this part. So we factor through this hyperplane. So I can sort of think of, instead of being the R to the R plus S, I can, this hyperplane is sort of just a codimension 1 subspace. So I'm sort of factoring through I'm mapped to a real vector space of dimension R plus S plus 1. Okay. And then what's the last observation? Oh, yeah, so the kernel is just the roots of unity. So this was basically an exercise on your worksheet last week. We're going to say something about it again in a moment anyway. But so the exercise last week was that sort of if you had some complex number, all of whose, or sort of, and this wasn't quite how it was phrased, but you have some complex number, all of whose conjugates have absolute value less than or equal to 1, and it's also an algebraic integer, then in fact it's a root of unity. So, but somehow that's exactly what it means to be in the kernel of this map. So if you're in the kernel of this map, that means sort of log of every absolute value for any embedding. So the log of any of these absolute values is equal to 0. So sort of being in the kernel, this means you map to the 0 vector here. But sort of log is 0, that means absolute value is equal to 1. So this is sort of saying that alpha is sort of all the conjugates of alpha have absolute value 1. Okay. So that's, yeah, by this exercise from last week is saying that's a root of unity. But we'll explain that in a second anyway. And so if you didn't do that exercise, you might want to stop the video now and just think about that for a moment. But we're going to need something slightly stronger. But let me sort of conclude. So we have, let's say where we're at right now. So we have L is a map, induces a map from sort of OK cross mod its torsion subgroup mu k to sort of a real vector space of dimension r plus s minus 1. So, well, if we can show that this is a lattice, and by the way, I guess what I'm about to call a lattice is probably inconsistent with what I was calling a lattice before. So here, when I say a lattice, I just mean sort of some finally generated Z submodule of this real vector space, which is sort of generated by vectors which are linearly independent over R. This is, and the main point is this is equivalent to having sort of a subgroup just sort of under addition. So it's equivalent to sort of having just a subgroup of this real vector space such that sort of if you take an open ball around 0, you only contain finitely many elements. So this is sort of equivalent to being a lattice. And this is something so we implicitly used when we were talking about Minkowski's theorem and when we were talking about class groups and finiteness of class group. And so, and even sort of before then, we sort of were implicitly using this other point. So, okay, but anyway, so here, previously when I was saying lattice, sort of I always meant a lattice of maximal rank. So sort of you were in a real vector space of dimension n, and you sort of had the thing stand by sort of n, like a set of basis vectors. Here, I'm sort of using this weaker terminology that's sort of just first we want to show it's just is sort of spanned by like the free module generated by some linearly independent vectors. So yeah, so we can show this is lattice, then we get that OK cross is finally generated with rank at most R plus S minus 1. And then, okay, and then the second part will be to show you have sort of maximal rank. Okay, but I mean, this is somehow easy because of this characterization I just said. To show it's a lattice, you just need to show the intersection with any open ball, just sort of some open ball around 0 has finally many elements. Okay, so and this is a good exercise to understand why that's true if you haven't seen it, but this is also somewhere in chapter 4 of Milne, if you just want to look this up if you're not familiar with this. Okay, good. that's basically free because if we're sort of in some open ball around 0, and here we can just sort of do it in R to R plus S. Okay, and then that means sort of the log of all the absolute values are sort of bounded by some constant. But then in particular, the absolute values themselves are bounded by that same constant, or not the same constant, sorry, by e to that constant. So that means sort of the absolute values are all bounded by a constant, but then sort of just like the things as elements of OK are bounded by that constant. And we already saw that OK is sort of a lattice inside of sort of the corresponding embeddings where we don't have absolute values and we don't take logs. So that gave us some embedding of OK as a lattice in sort of R to the R times C to the S. Okay, so right, well, if you fiddle around with that, then you see that because OK was a lattice inside of R to the R times C to the S, that bounded subset is going to translate back there to a bounded subset in OK that only has finally many things. So somehow it's not even, doesn't even matter about OK cross, like it's already true in OK for the image of OK under this map. Okay, so that's why. So this sort of follows from OK injecting into sort of R times C to the S as a lattice. Which again is something we sort of saw, sort of talked about when we were proving the Minkowski bound. Okay, so that's good. So we've now shown OK cross is finally generated, and it has rank sort of less than equal to R plus S minus 1. And okay, so now we just sort of need to show it really has that rank. So we need to sort of show it's of maximal rank. So this is sort of the interesting part, the most interesting part. Producing these units, you want to produce enough units to see the rank is R to the, sorry, is R plus S minus 1. Okay, so I want to do the proof in sort of just the case of real quadratic fields, just so we can see how this goes. And then the proof in general is not too much harder. So let's just see sort of for real quadratic fields. So this is like K is equal to Q squared of M, where M greater than 0. So this kind of equation we were looking at before, like A squared minus sort of MB squared, we want to understand like why does that have a solution where A and B, so A squared, oh yeah, so why does A squared minus B squared M equal plus or minus 1 have a sort of solution with B not equal to 0. So the only solutions, I mean, if B is not equal to 0, then it's going to be sort of something of infinite order because the only roots of unity will have are just plus or minus 1, so that would be equals 0. So that's what we're looking for. And well, and again, like we just need to understand, like, we need to see how that can happen. And of course, like if you're given an M, you can sort of just guess and check until you find one. Yeah, and so here, like to producing enough units just means if we can produce anything of infinite order, like we're just trying to show the rank is 1. So it's sort of, it suffices, we know it's less than equal to 1, so it suffices to just have anything of infinite order inside of it. So that's why it sort of suffices to find just 1 in this case. But again, like somehow thinking systematically how you prove such a thing exists is sort of a problem. Like it's not immediately obvious that there is always going to be a solution to this kind of equation. Okay, but okay, so how do you do it? So idea, well, you use Minkowski's theorem. You use Minkowski's theorem. Plus the idea I mentioned earlier of this pigeonhole guess and check. So what was the pigeonhole guess and check? Well, that said, I should just start writing down. Yeah, so let me scroll up to where we did that. So where I fake did that anyway. For q squared of 5, like I said, okay, let's just start writing down a and b's and sort of seeing what numbers we get. And like eventually we got some overlap. Well, sort of the first two examples, because that's why I chose this example. We got -4 and 4. And then, well, we know there are sort of only so many ideals of norm 4. So we took their sort of, if you sort of kept on doing this, you got enough of that, like enough things you got enough things whose norm was 4, like eventually they're going to have to differ by a unit. And well, we just checked, so we took the quotient of these first two and they did differ by a unit. They differed by a unit, and so that was sort of, that gave us our unit. Good, so that's what we want to do. And we want to sort of implement the same procedure where we're sort of going to like guess and check until we sort of hit a bunch of things with the same norm. And sort of once we hit so many, like once we hit enough, like the pigeonhole principle will tell us sort of 2 of them are generating the same principal ideal. And then so they have, their quotient is going to be a unit. And that's sort of, that will solve the trick. So to do this sort of precisely, to like really guarantee we can get things, we can get enough things of the same norm, we want to use Minkowski's theorem. So that's sort of what will help us here. Okay, so okay, so let's look at this. So how do we do this? So Minkowski's theorem, so we have sort of this q squared of m is sort of living in sort of r squared. Really OK is a lattice in here. And here, because there's no complex embeddings, the volume of fundamental domain is just the square root of the discriminant, which is either 2 times the square root of m or just the square root of m. Okay. So we have this lattice inside of r squared. The volume of the, yeah, okay. We have this lattice inside of r squared. And let me sort of take T to be any sort of convex symmetric subset. Big enough to contain a point. So big enough, sorry, with big enough area. That Minkowski's theorem guarantees it contains a point in OK. So Minkowski's theorem means not the like Minkowski bound, but here just the Minkowski's theorem that said if you had sort of a lattice and you had this convex symmetric region of area sort of like here, I guess we need it to be 4 times the area of the lattice. so 4 times the square root of the discriminant, then it's always going to contain a non-zero point of the lattice. Okay, so we're going to do this, and right here, let's just take t. And we could, so here's okay. I don't know, like maybe it looks like this. So here's sort of lattice points for okay. Then we could sort of take t to be just like a unit, like a ball of sufficient radius. So this is t, and then sort of the purple dots were okay. Okay, good. So that's, maybe I should take my, looks like my thing almost doesn't contain. Okay. Okay, so that's my ball. Okay, and so good. And then what I'm going to do is I sort of, let me observe, and the norm, which is just sort of in terms of like R2, it's just xy maps to xy, is bounded on T. Okay, so let's say sort of by m, just some number m greater than 0. Okay, but now we're going to sort of use this cool trick, which is if we look at sort of, whoops. Okay, good. I don't know what happened there. I guess I lost some stuff. I think it crashed. Okay, so well, okay, so yeah, let me just write that again. The norm is bounded on T. So n of x, y is just the product x, y. So you sort of somehow OK is put inside there, and sort of the norm on OK just becomes the product of the two coordinates, because the embedding is just sort of the product of the two embeddings. Okay, so this is bounded on T. But actually, sort of, we're even better because we can't sort of, the trick is that this doesn't just work for T, this works for any sort of suitable scaling of T. So if I look at sort of the number 1 over R, so I look at sort of 1 over R, comma R times T, then so this is sort of a new region where I sort of just scale. So this looks like sort of, I sort of squish it down. So I'm sort of, whoops, and squeezing it together. So I'm sort of multiplying the x coordinates all by 1 over R, so they're getting small, but then the y coordinates are getting sort of mapped by, scaled up by R. So it's sort of, they're getting bigger. So I'm sort of squeezing it and stretching this region. Well, this has the same volume. And the same bound on the norm. Okay, so this has the same volume, the same bound on the norm. So, and it's still symmetric and convex. Okay, so in particular, sort of so let me just sort of look at like 1 over n times t, so n sort of in positive integer and a natural number. Let me look at these things. contains an element by Minkowski. And so because this volume, the volume of T, which is the same as the volume of this set, is enough for Minkowski to apply, contains a non-zero alpha n in OK. Of sort of norm of norm less than or equal to m. But so there are only finitely many ideals of norm less than or equal to, sort of, let's say, I sort of k of norm less than or equal to m, and sort of, and there are only finite ideals, and particularly only finitely many principal ideals. Okay, and well, so let's sort of just say like I1 is equal to sort of beta 1. Let me just fix a generator for each of these. Ik is equal to beta k. Okay, and so like if I look at sort of the coordinates of beta 1, beta I is equal to sort of xi, yi, well, there's sort of a minimal x coordinate for these I equals 1 to k. And then like if I sort of make my region thin enough, so if I sort of take n large enough, my x coordinate is sort of going to be sort of very close to 0, and so it's sort of going to be closer to 0 than it is for any of these guys. Okay, and so, I mean, yeah, sorry, these are all non-zero because they're given sort of from the embedding of an element, from an embedding of OK into R. Sorry, of K into R. So then what that means is sort of alpha n, or sort of n sufficiently large, is not equal to beta I for any I, but it generates an ideal of norm less than equal to m. So there are only finally many principal ideals of norm less than equal to m. So, but sort of alpha n is equal to beta I for some I. So alpha n over beta I is a unit, and like it's sort of not equal to plus or minus 1. So it's not a root of unity. I mean, somehow it's basically by construction, it's not a root of unity because you can check sort of, I mean, sort of its x coordinate is not going to be 1 because sort of by construction, I sort of took this alpha n, so it had different x coordinates, different smaller x coordinate than beta I. Okay. Yeah, good. So its x coordinate won't have absolute value 1, so it sort of can't be a root of unity by this earlier characterization of roots of unity. Okay, so good. That's the idea. So that gives you that this is of infinite order, and that's all we need to show. We need to find one unit of infinite order. Okay, and now sort of you see also basically how the proof goes more generally. I mean, the first part we already had set up. sort of put this embedding to R plus S minus 1. And well, you can just sort of run the same kind of argument where sort of to get sort of independent units, like you scale, so you squeeze in the X direction, like in the first coordinate direction, you squeeze in the second coordinate direction, and so on. And sort of, well, if you, it's not so bad, and it's a little bit of linear algebra in the end, just to sort of do that and then sort of squeeze enough in each direction that you get sort of things that you can check are linearly independent after applying this this logarithm of the absolute value map. So that's how the proof goes in general, and you can look at the details in Milne if you'd like. Okay, but I think I'm going to stop there for this lecture, and I'll see you all in class on Tuesday.